Okay, thank you, Diedert, for this nice introduction, and thank you all for joining this webinar. As you probably have heard before in the context of the MICAT tool or in other contexts, the motivation for developing such a tool is just that in traditional cost-benefit analysis, there is a danger of underestimating the benefits and overestimating the cost, and then you get to skewed results. And that's why we have developed this tool. This is a project in which we are aiming to address or sort of to cover multiple impacts of energy efficiency measures to get to a really true assessment of what the benefits are. When we talk about multiple impacts or multiple benefits, this is often in literature sometimes called co-benefits, and that relates to, as I said, a long range of literature that tries to assess these. I'll briefly sort of just remind you of the fact that the MICAT tool is a project that was funded by the EU, or has been funded by the EU, and it builds on previous methodologies and previous projects developed on other projects. We have improved the methodology. We have started to engage with stakeholders at the national level, at the city level, and at the EU level. And the coverage of the tool is such that we cover really all pillars of sustainability, namely economic aspects, social aspects, and environmental aspects. The aim of the tool is to really maximize the usefulness for a large target audience to be able to assess what the multiple impacts of energy efficiency measures really are. The general approach in this tool is that we have various dimensions that we can cover. We can do ex-post analysis at the very detailed level, but we can also look into the future and look at future scenarios, future situations. So we can assess ex ante what may happen as the result of introducing energy efficiency measures, but we can also assess ex post what the impact of interventions or policies have been. The general approach that we take looks like this is a little bit of a busy graph, but sort of conceptually what we do is we sort of start here on the left-hand side, where eventually the user will be able to enter into the tool the kinds of measures that will be taken to save energy and the amounts, and then this will be translated moving from left to right into impacts or benefits or avoided impacts, if you like. These will be then monetized, and eventually the monetized benefits will be compared to the costs of the proposed measure, and so we can really come to a complete or comprehensive assessment of the costs and the benefits. What is behind the tool is a lot of data that come out of, well, it's called here the literature. It's the latest scientific understanding of what the various impact factors are. This involves also some modeling, and I'll come back to that in a dedicated slide for particular environmental impacts. And these are then really distilled into specific factors that can be used in a simplified tool that is much faster and more responsive than the sort of the state-of-the-art tools that are typically run and operated by the researchers themselves. Okay, so this gives you again, this is repetition a little bit of what was said what was said in other seminars as well, to give you a context. Today we will now focus on the environmental indicators that are covered by the MICAT tool. And I first want to clarify the scope. When you think of the environment, there are many things that you could imagine that we are addressing, ranging from air, natural material resources, water, waste or soil, and then all the way up to biodiversity. In MICAT, we restricting ourselves to a number of indicators that are related to air and natural material resources. This again is not to dismiss that the others, or sort of to say that the others aren't important, but it is a way just reflecting expertise that was brought together by the modeling team. And of course, if the modeling team had been bigger and more diverse than, and the project bigger and better funded, if you like, then we would have been able to cover other aspects as well. But also, when it comes to biodiversity, of course, this is a really, really complex area, and it's in a sense also doesn't lend itself to be put into a framework model that allows you just to work with very simple mechanisms to get first order estimates. So we draw the system boundary. Nevertheless, we are very thorough in assessing the aspects that we are covering. I'll go through these indicators related to air. I'll focus a little bit on the air because this is my area of expertise, and only touch upon the material resources towards the end. What I will do is I will sort of explain a little bit what the issue is and where we're coming from, and explain a little bit what the regulatory framework is. And then I'll tell you a little bit what MICAT can actually do. So broadly speaking, in general, what we always do in MICAT is that we kind of estimate what is the footprint for the various indicators, whether for greenhouse gases or air pollutants or material use. We calculate the footprint for each unit of energy, and that allows us to then, quantify the benefits for given interventions. Okay, so just to give you an overview, again, what we do, this is a little bit more boring than the figures before, but what you can see here is sort of our internal list of the indicators that we are covering. On the one hand, there are, of course, when you save energy, there are, of course, directly benefits in the sense that you are saving energy. That's physical material, and energy has a cost, and therefore that is a benefit if you save energy. But then on the second point, you save material resources, and as I said, I'll come back to that. We have a few subcategories that I will go into in a little bit more detail. And then on the side of global and local air pollutants, we're thinking primarily of greenhouse gases in the sense of CO2, and then reduction in air pollutant emissions. And sort of in between is this renewable energy systems target that also is affected by by energy saving measures. Again, that's something that I will not focus on because that's not really my area of expertise. Now let's focus a little bit more on the air pollutants, and I'll briefly explain explain how this is actually calculated in MICAT and the level of sophistication and detail that is encoded in the tool. So it's relatively sort of focusing on the left-hand side. MICAT is relatively straightforward in what it does. We simulate an intervention, which means that we have some energy savings measure taken. And this now has, or it can have, essentially two direct impact. Namely, it can change the amount of direct energy that is consumed, directly combusted, but it can also reduce the electricity consumption. So typically, for example, if you insulate a house, then what happens is, on the one hand, you're reducing the amount of energy that is being used to heat the building, and that is typically done through direct combustion, through a gas boiler or oil boiler or biomass boiler in your basement. But it also changes the amount of electricity that is being consumed, for example, because in the summer you may not need to cool it that much, so your air conditioning runs less, and so you save electricity. So both of these effects are taken into account, and so we change the energy consumption, the direct energy consumption, and electricity consumption. And depending on what kind of device you're using and which emission standards that device adheres to, this will have then implications on the emissions of pollutants such as sulfur dioxide, NOx, and PM. So again, it's very straightforward. The key really is to understand what are the emission standards, what are the emission factors that should be used. And in order to assess this properly, we're using for MICAT also the GAINS model. The GAINS model is an online tool that is developed at my institute, the International Institute for Applied Systems Analysis, or IIASA. And it's been developed over the last 30 years or so. We are supporting with this model. The model has been used to support the European Commission in devising new legislation on air pollution. So it reflects all the legislation that is currently in place and is planned to be in place in Europe in future years. The model has been applied not just in Europe, but in other parts of the world as well. And we're not just working with the European Commission, but also with individual countries to improve their data that go into the model. So in summary, we're using kind of the state-of-the-art tool, and we are completely consistent with the legislation that is in place in the EU. Everything that we do reflects already what has been developed elsewhere as well. So then the question is, in general, so how in GAINS, again, let me dive a little bit deeper into this. How does GAINS actually now calculate these emission factors, or what needs to be taken into account? And I want us to look at a specific example. So typically what we calculate when we look at emissions, we calculate this as a function of the activity data and some emission factor. So activity data is the amount of fuel that you're using, and the emission factor is the amount of emissions that you get per unit of fuel. So in the example of a coal-fired power plant, what you do is calculate emissions by multiplying activity data with an emission factor. So let's say you look at all the power plants in a particular country, that's 100 petajoules. What is it that you need to multiply this number with? Now, as I said, the emission factor, the value of the relevant emission factor depends on the control technology in place, and the technology in place depends on the legislation. So here's an example of the values of the emission factors that are part of the GAINS model. Different technologies here on the left-hand side are associated with different emission factors. In the uncontrolled case, we have a very high emission factor, and if you're choosing a high efficiency scroll, then the emissions are very close to zero. So amongst these technologies, which ones should we use when we do our calculations in MICAT? And the answer is, again, it depends on the emission control technology that's actually being applied in the real world. And what is being applied in the real world depends on the policy context. Now, just as a reminder for you of what we have in place in Europe, we have a number of legislations that control the emissions of air pollutants by different sources. We have overall some strategic documents like the Zero Pollution Action Plan. We have a National Emission Ceilings Directive. And we have directives on various types of plants and industrial installations, and so on and so forth. Some of these policy frameworks are very specific on what emissions can come out a stack of, let's say, a power plant. And this is reflected then in what we call here a control strategy. A control strategy is just a mix of technologies that produces exactly the emission factor that is consistent with a given legislation. So for example, here's just sort of on the right-hand side, this is an illustrative example that we have a non-trivial fuel mix of 3 or 4 different technologies that make up the sort of the average installation of different technologies across the fleet of all power plants. So when we calculate then an emission factor, what we're actually using is an average emission factor, so a weighted average emission factor that takes into account the different underlying elements, the different technologies, and the relative shares to which they are used. And this was now the example of, let's say, a coal-fired power plant, where we can do this for all relevant sector activity or emission source categories for each country, again, completely consistent with what we do for the European Commission. So, so if we then go back to the emission calculation, what we also do in order to calculate emissions, we calculate how much coal is being used, we multiply this with the emission factor, or rather with the weighted emission factor weighted by the penetration rate of the different technologies. And if we want to calculate the benefits in terms of emissions of reducing the amount of coal, then we just read off what does 1 unit of coal produce in terms of emissions, and then we scale it with the amount of energy that's actually saved. Then we can do this for all categories. Here's an example for vehicles. Now here for vehicles, so gasoline cars, for example, the situation is different. The underlying fuel is now different. We're looking at gasoline. The emission factors are very different. We're now referring to Euro standards. And here we're now looking at NOx, for example. And the penetration rates of these Euro standards is again very idiosyncratic, very, in each country it is different, and it also depends then, of course, on the time, because the share of the technologies changes over time as new Euro standards are introduced as part of the legislation. Good, we can do this for all pollutants, just to illustrate that, of course, each pollutant has a different set of emission factors, has a different set of control strategies, and as I said, these control strategies change over time. The penetration rate of different technologies can change over time because new legislation comes into force in the future, but also there is a fleet turnover. Think again about vehicles. Old vehicles that were subject to Euro 1 standards are slowly phased out over time because they're getting older, and they're being replaced by newer cars, and these new cars then obviously, of course, reflect or adhere to newer and more tighter emission standards. So again, all of that is being reflected. And so with this, we are now able to calculate for a given year and a given intervention, so for a given amount of fuel being saved in a particular sector, we can now calculate what are the benefits on the emissions of different air pollutants. Now, how does this help MICAT, or how is this actually a benefit? Now, what I said already, actually I presented some of this work already last time in the previous seminar, which you're free to look at. But the main point of air pollution is we're not really interested in the emissions, but the real main point of air pollution is that it has an impact, and it has an impact on their lives and of the health of people. So here's a little bit of a repetition from last time. The EEA has estimated that still in 2021, we're talking about 240,000 deaths still being caused by bad air in Europe. And so what I'm trying to emphasize here is the main objective here, or the main impact or the main benefit, actually comes from reducing these deaths, and reducing the emissions, in a sense, is just an intermediate step. And that's why we do not quantify the benefits, so we don't cost or monetize the reductions in air pollutant emissions as such, but rather we follow them all the way down and see what kind of impacts they have. Different impacts have different emissions, and if we are now reducing energy by energy efficiency or energy saving measures, then we can see these benefits going through the cause and effect chain all the way down to the impacts. So as I said, I've shown this last time. We can really, on the basis of this framework and the data in the gains model, we can sort of now not only calculate the emissions that are being reduced, but we can then see how these reduced emissions spread out, or rather how a reduced emission scenario would sort of impact air quality in different parts of Europe. We then can overlay this with a population density map that figures out where people live, and then figure out how many people are actually affected by what kind of air pollution, and how many people are susceptible to what kind of diseases resulting from pollution levels at different locations. And this allows us then to assess the number of premature deaths, for example, or days of work days lost, and so on and so forth. So this is sort of the standard cause and effect chain that is being reflected here in MICAT as well. I've said last time already that we monetize these benefits in terms of work days lost, hospitalizations that can be avoided, and avoided premature deaths that are all multiplied by the very specific cost factors to be able to enter the cost benefit analysis. In the overall approach, and again, this is summarizing both the emissions as well as the whole impact calculations. We make some sort of central assumptions, and one of them is that what we should be focusing, or what we are focusing on, is fine particulate matter, or PM2.5, and its precursors. There are other air pollution related problems that have significant impacts, but they are sometimes one or at least half an order of magnitude smaller when it comes to monetization. That's why we are focusing on this main impact. And what we also have as central assumptions is a whole framework, as I said, that is completely consistent with legislation or regulation that is currently being discussed at the EU level. Now, this is as much as I wanted to say about air pollutants directly. I can say a few more words about greenhouse gases, in particular CO2. Here we're following exactly the same logic from an intervention, splitting out the difference in direct consumption and electricity consumption depending on the measure, and then depending on what the various emission standards are, or actually the fuels that are being used. Not talking so much about emission standards, but different fuels, obviously, and this will then lead to different emissions in CO2. So we have associated CO2 savings, and the way that they are reflected in the cost-benefit analysis is now that we monetize the CO2 emissions, and there are at least two ways of doing this. We leave it to the user to specify the kind of values they want to use, kind of the kind of pricing factors, if you like, in the cost-benefit analysis. But some guiding principles could be to look at the value of carbon in current carbon markets or future carbon markets. So you would be looking at carbon prices arising out of empirical markets or price projections from these markets, to get some idea of what the value of the CO2 being reduced and what that would be. Another alternative is to use what is called the social cost of carbon. The social cost of carbon basically takes into account the negative climate impact that a ton of carbon will have in the future. So today there may be no harm, but we can calculate that CO2 will lead to a very, very small, a ton of CO2 will lead to a very, very small increase in temperature in the future, and this will cause marginal impact on the damages arising from climate change. This can be estimated, can be monetized. People have done this, and they come out with an estimate of what the carbon impact, what the value of a reduced ton of carbon would be. And this is again summarized in this concept of the social cost of carbon. Again, there are different estimates of how high these values should be, and again we leave it to the users to specify them. We can have a default value, but in principle users can specify this in the tool themselves. So central assumptions here on CO2. We use IPCC Tier 1 emission factors. This means in particular, and this is a little bit maybe of a shortcoming, but it's not a big thing, that we, for example, do not take into account that, that certain oil types have different carbon contents, and so there's a little bit of a differential carbon content in different types of fuels. There's the question of whether the fuel is combusted completely or not. These are all minor or marginal changes that will not affect the main picture. The main thing that is important is to understand whether the fuel that is being saved is either gas or oil or coal or biomass or renewables, and this is reflected correctly in the MICAT tool. Biomass we do not consider to be carbon neutral. This is something that has been discussed for a long time, whether one should treat biomass as carbon neutral fuels. We believe it is too optimistic to assume that it is carbon neutral, given the effects that happen all upstream, and also given the effect that while in the long run biomass can be recovered, but the carbon in biomass is long-term stored carbon from the atmosphere. The time frames over which this happens is just much longer than what we typically consider in the policy context. What we do not consider in MICAT is non-CO2 gases. Some obvious cases could be that one considers, for example, if we save a lot of energy, we may reduce, let's say, the amount of gas that is being produced, the amount of gas that is being pumped through pipelines, and that would lead to a reduction of, say, leakage of methane. The trouble is a little bit, and that makes it really complicated. It's not impossible, but complicated. Is really, you really have to understand very well where the gas in different countries comes from, which pipelines it runs through, where it's being produced, how it's being shipped. And we all know that these things can change rapidly, as we have seen in recent months. So we do not cover this non-CO2 gas effect. Certainly something that could be looked into the future. But again, what was important for us was to understand better the relative importance of, let's say, the CO2 effect versus the air pollution effect versus other social effects like energy poverty and so on and so forth. So certainly something for refinement, but not in this project. Okay, and this brings me to sort of the last point, or the last area that is being covered under environmental indicators, and that is the savings of natural material resources. Here I've already mentioned what we're actually doing is we are calculating, if you like, some kind of material footprint in MICAT. And for different kinds of interventions, we calculate not only how much fuel is being saved, but also what part of that is fossil fuel, And if we are saving fossil fuel, what does that mean for the upstream energy system? So for example, and I jump a little bit here onto the bottom of the approach. So for example, if you're reducing electricity, if you're saving electricity relative to your baseline scenario, if you like, or your reference scenario, what this means is that you have to, for example, to build a power plant less. And this could be a gas-fired power plant, or coal-fired power plant, or a wind turbine, or something of that sort. And that means that you don't need to build it, which means that you don't need the resources, the mineral resources, and so on, that actually are used to build the plant itself. But it also means then, of course, that you don't need to, not only do you don't need to burn the fuels that would normally be used, but you also don't need to extract the fuels. So we have sort of these two components. We have the use phase. So we have the production phase, as it's written here. We have a production phase in which the actual installation, the conversion equipment, the energy hardware, so to speak, is actually being produced. And then this is if we save energy, then we can save that amount of materials that go into the production phase. And then in the use phase, once you operate a plant, you're using materials as well. For example, resources extraction for fossil fuel production. So both of these factors are taken into account. And so we are kind of calculating for each intervention an approximate impact on the resource use and the extraction amount, and so on and so forth. And so when we save energy, we multiply this with this impact factor and get the amount of impact that is being reduced. So again, here's sort of a rough picture of how this goes. We sort of start out by assuming, or the user provides us with the amount of energy being saved and an energy mix. This allows us to sort of see how the different stocks are changing, what kind of resource extraction can be replaced by nothing. So this is this unused extraction, if you like. So and this is now split into a production phase, into a use phase, and then aggregated again into a marginal impact factor that takes into account all the material use reductions up to that calculation level. And then the natural resources are, the savings in natural resources are calculated by comparing kind of the pre-action scenario with the post-action scenario. So you compare a situation in which you save the energy with a situation where you don't save the energy, you do all the difference calculations, and then you find out what the relative savings are. Good. And so then you have sort of a representative energy efficiency improvement action, and so for a limited number of energy efficiency actions in MICAT, we make that estimate of how many resources are being saved. For example, in the case of lighting and in the case of electric vehicles, this is done by understanding kind of life cycle analysis and international trade patterns. The resource savings themselves are also not included in the cost-benefit analysis, a bit like in the case of air pollutant emissions, because we want to avoid double counting, and the investment. So there's a danger of double counting, specifically in the context of the economic indicators, where we have looked at investment requirements, and the cost savings, of course, are covered in the energy costs, not as environmental costs. Good, and that sort of summarizes the main points from the resources assessment as well, and that brings me also to the end of my presentation. And I guess I'll just hand the floor back to Diedert to